So now that we've talked a bit about the fundamental theorem of calculus, we can revisit uh, some of the topics that were done back with derivatives. Specifically, if we're given graphs of a function or a graph of the derivative of a function, uh, we can now revisit this in terms of thinking of it in terms of integrals as well. So here we're given a graph of f of x, and we're told that h prime is equal to f, and that our function h is going to have to go through the point 0, 0. One thing I would definitely suggest is, as you can see to the side here, we're going to be talking about some questions involving the function h, but the graph is labeled in terms of f. So it'd be really nice if we, to remove a distraction for our thinking, relabel this graph to be in terms of h. Well, we're told that f is equal to h prime, so this is really the same as saying this is a graph of h prime of x. Which actually means we can talk about finding extrema and points of inflection at this moment. We don't even need to know anything about h, because we're told h prime. So for extrema occur at endpoints, so we could have an extreme value at 0 when x is 0, or at 8. They also occur at critical points where h prime would be 0 or undefined, which in this case would be at x equals 1 and x equals 4. If we look at critical points first at h prime of 1, or at x equals 1, h prime does not change signs. H prime is positive values on both sides. So if I'm thinking in terms of a sign chart for h prime, it doesn't go on forever, it goes from 0 to 8. At 1, h prime is positive to the left and positive to the right, so there is no extreme value at x equals 1 for h. For 4, to the left, h prime is positive, and to the right, h prime is negative. So we do have a relative maximum at x equals 4 because h prime is changing signs as x increases from positive to negative, meaning h is changing from increasing to decreasing. Remember, for your justification, include the behavior of h prime and h in your justification, and also be sure you're avoiding using pronouns. As you notice, I've been saying h prime and not it. In terms of our endpoints, 0 is the left endpoint, and to the right, h prime is positive, meaning h is increasing. So we have a relative minimum at x equals 0. At x equals 8, that's 8 is the right endpoint, and to the left, h prime is negative, meaning h is decreasing. So we have another relative minimum at x equals 8. Now, because this is a closed domain from 0 to 8, and I can tell since h prime exists for all points there, that means h is continuous from 0 to 8, the EVT applies, and there must be an absolute max and an absolute min in this. Because the only relative max is at x equals 4, this must also be an absolute max. But then I have two relative minimums, and to decide which one is absolute, I need to actually be able to say something about the values, the h values at the endpoints. Well, we're told h of 0 is 0, so I need to talk about h of 8. And this is where our fundamental theorem can now come into play. If we go back here to where we're discussing that h prime is equal to f, and I need to start talking about finding out what's h of x, what's h of 1, or in the case for absolute minimum, what's h of 8, so I can compare it to h of 0, I need an equation for h, which means I need to undo the derivative. Well, from the fundamental theorem part 1, undoing a derivative means we're taking the integral, which would give me h of x as the integral of f of x with respect to x. But instead of using x's from FTC part 1, we know that x should be the upper bound. I'm going to use the dummy variable of t, within the integrand. Remember, t doesn't actually represent anything, it's just a placeholder for x, since for technical reasons we can't have x in a bound and in the integrand at the same time. In order to guarantee that my function h goes through 0, 0, the lower bound is the x-coordinate of the point it must go through, and plus c is the y-coordinate that h of x must go through. So now that I actually have an expression here for before I get to h of 8, let's talk about h of 1. Well, h of 1 means I'm replacing x with 1, so I'm doing the integral from 0 to 1 of f of t dt plus 0. Well, I can't find h of 1 exactly because I don't have an equation for f in order to use antiderivatives there, but I do have the graph of f. And graphically, the integral from 0 to 1 is finding this area, which will be positive because I'm above the x-axis. So I'm going to be estimating h of 1 by estimating this area. And if I use a triangle to estimate that area, I get h of 1 is about a half. Now for the absolute minimum, I need to talk about h of 8. Well, I know h of 0 is 0 because we were told that. For h of 8, that's the integral from 0 to 8 of f, which means I would use this area, I would need this area, but then I have this big area underneath the x-axis, meaning this will have a negative value. Because the area underneath the x-axis is larger than the areas above the x-axis, my derivative, or my integral value, is going to be a negative value, which means it's going to be smaller than h of 0 then. So therefore, the relative minimum at 8 is going to be lower than the relative minimum at 0, which makes the absolute minimum occur at x equals 8. Then to just kind of finish out the questions we have here, if I wanted points of inflection for h, all points of inflection occur when concavity changes. Concavity changes when the first derivative changes from increasing to decreasing, or vice versa. Well, since I have a graph of the first derivative of h, where h prime is increasing, h is concave up. Where h prime is decreasing, h is concave down. So where h prime is changing directions is where I'm going to have a point of inflection. So looking at my graph, I can see that I'm going to have a point of inflection at x equals 1, x equals 3, and x equals 6. Because that's where h prime, the first derivative, is changing from increasing to decreasing, or from decreasing to increasing.